All right, so hello everyone. So I want to make a little follow-up video to that last one because we were having a little bit of issues getting the getting that source term to work out. So just kind of a recap what we've been up to. So we've had this kind of two systems. One side has our negative reactance. One side has our positive reactance. So our negative reactance, right? So we have our reactant, which was V2 plus, at least this is during discharge, and we have our product, which is V3 plus. And so what's going to come in is we're going to lose V2 plus at this surface, and V3 plus is going to go away. So you're going to see this concentration is going to go down at the surface and propagate through, and this one's going to go up at the surface and propagate up. At the same time, on the positive half side, you have your reactant VO2 plus, right, plus 2 protons. They're going to come in and they're going to react. So both those concentrations will go down as you discharge. And what's going to come out is going to be VO2 plus plus a water molecule. So you'll see those two concentrations go up at the surface. And so that's what our cell's modeling. And what we want to say is, like, okay, so what we notice with this is, let's say this is our V2, right, is what's going to happen is it's going to stay high concentration over here, and then it's going to dip at the surface. And when the surface gets, this concentration at the surface gets so low, below, we did concentration versus time, and it crosses 0, then this is where the cell dies, right? So you have basically no more reactant on that left-hand side to react, and that seems to be what's killing our cells. We said, okay, well, what you normally do in a flow battery is you'd flow some reactants in there. And so if we look at this left-hand side, so our model, right, so we have this is our reaction spot, right? So this is where we're basically removing V2. So we're taking V2 out at this point, right? And we're putting V, right at the surface, we're putting V3 plus in. So that's our boundary condition. Here, there's a wall, so there's no flux at that boundary condition. And what we've done is we've discretized this in one dimension. We have points that go along here, right? And so what we can do is when we model this, these are kind of, you can think about these as little chunks. One sec, I have a guess. So we, sorry, let me share my other screen. So we were talking about breaking up these into different nodes. And so, but also at each one of these nodes, there's a certain velocity going in, right? And that velocity has to be the same as what's going out unless it's compressible. And so the way we see that adds to the flux is you have the velocity times the concentration of what's going in times, so this has some width, dx, we know. This has some height, h. So this is going to be dx times the height going in, and what's coming out is going to be v times c, the actual concentration of this point. So this is in. So concentration of this point, p, I'll say, which is that point, times dx times h. And so the difference between what's going in and out, which we'll want to do on a per volume basis. So kind of our source term will be like delta, we'll just say it's in minus out over volume, because we're doing everything on a per volume basis. So that's going to be velocity times c in minus c of this point times dx times h. We have to divide by the volume. So the volume, though, is dx times height times the width. Right. times the width. So all you're left with here is the width. So for us, if it's square, this is your area to the half power, which I think we'll do. So, and then we said last time, let's see what's going in. You could say it's the fresh stuff, but see, and it could be your initial concentration of that. And then if it's, for example, if it's, let's do the example of V2 where it's being consumed, this is going to be decreased as the total amount. So this current, so that's coulombs, and then we're going to have times change in time, and then you're going to have times NF, but N's 1 in this system, and F is Faraday's constant, which is coulombs per mole, right? And so this is going to be IT over delta volume, or sorry, IT over volume. This is the volume of your tank, so V volume of your tank, right? And then the only other thing we did is we said, hey, we know the velocity profile going into this needs to be parabolic. So it's going to be velocity versus this position x. So we'll call this like position x in this diagram. We know it's 0 at this wall, and it's going to reach a maximum in the middle, and it's going to go over here, be 0 here. And this will be our V max. And so if this has some length L, the velocity V, so that's this distance up here. So this is V as a function of X. So velocity as a function of X can be our max velocity times 1 minus, it's going to be 1 minus the distance from the max. So the distance from the max is going to be equal to, it's going to be your X position minus length over 2. So so if it's here, this is L over 2, this is X, this is that distance, you subtract them. Then you divide that, then what you want to do is divide that by the whole distance away you can go, which is L over 2. And this term is going to be squared. So that's the parabolic profile. So you're going to see, we're going to implement those two in the code, and you'll see how those work. So I'm going to stop sharing this. I'll go over and share this screen. So in the code, so you'll notice this one will be slightly different than where we ended last time when you find it. One, there's a couple global variables. So that means you can define them up here, and then you can pass them into your functions, which is nice because I like to define everything up here and then pass them in. That way I don't have to go and look for them. So Faraday's constants up here. I put in a max velocity and the volume of our tank here. So, so this is volume of the tank. So, and channel. So we'll just say it's the volume of those two combined roughly. Although the channel volume should be much smaller than the tank. So it should be close to the tank basically. But if we include this actual channel we're modeling in there, we can just say this will be the volume for everything. So we solve our time, everything else is the same. Solve for all of our overpotentials. Then we look for when the battery voltage goes under 0.6 and we call it dead. If it goes under there, we solve for the total energy we got out and the power. If it never reaches there, then we just say it's just time that it ends. We'll just say what was the total energy and power, but we didn't actually fully discharge it. We need to run the simulation longer. And the reason I do this first now is we can actually plot things 0 to when it dies, right? So make like these plots look cleaner. They don't actually go back up. So you can put in this X lim, which says the bound. So it goes 0 and T death must have been like 35 seconds. So we scroll down. So the actual place where the code is inputted. So I don't have to add this velocity on the edges because the velocity is 0 at the edges. So I don't need to modify these. But so here I have my V max. I have my X times dx. So X is not the X position, it's just an integer. But X times dx, that's actually your X position. The reason this didn't work before is instead of rounding these to an integer, we said integer 16, which meant when we used it in here, this X in here, or when we used the X here, or no, we used NX actually. When we use NX in here, X also has an integer 16. That's the type of character it is. That describes like, like 16-bit rounded to an integer. And then but then when you did a calculation here, that made this an integer, the way it was. And so it would have kept rounding it to 0. So that's why we kept running into trouble. It was this weird way we did this rounding here. And then the C of the tank, so this is the initial minus the current times T is not the actual time, but T times dt is divided by volume times F. So that's what I just showed. And then the source term is just these two multiplied together, right? So we said this was just going to be, it was going to be so we have the concentration of the tank minus the previous, right? So that's the concentration. This is concentration in minus what's in there. So that'll be going out. And I just divided by the area. So that's kind of the height of our channel, or the width of our channel, I guess is what I said, times the velocity. And then all I did was I added that as a source term. I added this source term, and then I tracked it. So you can see, because I had to declare my global variables to pass them into here. So I declared source, Vmax, volume, and F. So I can pull them from above. And it's also nice because I can find them in here. So if we run our code, this normal way. So these are pretty small right now, like no velocity. And you can see this is why I just ran it. It kind of dies around 35 seconds. Scroll down, you can see why it dies. So these ones still, you can see VO at about 100 seconds runs out, but you see even less under 100 seconds. This is probably like the end of the simulation. This V2 runs out. So this V2 runs out at about, must be around 35 seconds or so. So right here. So it must be closer to here than it actually looks to me. So somewhere around there. And then you can see the concentration of the V2, and you see how it goes negative at some point. So let's instead now, so I'm going to use so what I can do now is I can try and use this to refresh this. So let's say now I'm going to have some Vmax. So now I'm going to have some velocity. So this is like 1 millimeter a second. So let's try if I flow the velocity. And I have a pretty big volume of the tank right now. It's 10 milliliters. It's quite a bit bigger than the actual channel. So this will help refresh it for a while at least. So you can see in this live script how it's running the code. Okay, very close. So here you can see it lasts a really long time, and it would just reach a steady state, but this is actually you're using up the material slowly. So you can see now when you do the velocity, you can now use all your volume. Before it was just diffusion. So we scroll to look down here, so you can see it's steeper at the surface here, but not quite as steep as before. And that's because we're helping get fresh stuff back, and it's not just depleting all the way through like it did before. So now let's say, hey, but now we don't have like an infinite amount of solution coming around. We need to shrink our tank size. So let's even -6. So this is like if we only have 1 milliliter. So let's try running it now. Let's see the effect. So this could help you, and you notice that this power value and this energy value are going to change. So energy total this last time was 55 joules. So this is in joules. We should notice this should go down by quite a bit because we've reduced the size of our tank by a factor of 10. Before it didn't completely die, so we might not see it go down by a full factor of 10. Right, it only went down a factor of 2. That's because it's actually dying this time, so it should actually have more. So what you see now is now not only do you have this not only do you have this velocity that's helping refresh it, but you also are running out. And so that's why you see these kind of reach this kind of approach. And you'll see how this is slanted down. And at some point, they slant down and it dies. It'll die a little earlier because now you're running out of fresh solution, basically. So yeah, so that's kind of what I wanted to show and where we were at from last time. So good luck getting to here and applying this to your next code.